So let's continue on. Let's talk about some more ways to compute some limits. So what can we do? Well, last time we talked about limits, and you might have noticed that if you just took the functions we were trying to take the limits of, it's very important to learn how these things work because things are going to get more complicated, but indeed, you could have just plugged the numbers in and gotten the correct answer in those cases. And that's true, we just use them to get a practice on how the limit laws work, but let's note that this isn't always the case, because let's do the following example. We'll first talk about it, then we'll go through it. Let's take the limit as x goes to 2 of x squared minus 4 all over x minus 2. Now, of course, x squared minus 4, not a very complicated function, and x minus 2, not a very complicated function. But if we plug 2 into those, well, up top, we would get 2 squared minus 4, which is 4 minus 4, which is 0, and we get 0 in the bottom as well. And guess what? You can't divide by 0, so this isn't quite going to work. So if we wanted to do something like this, we need to do a little bit of algebra on it in order to make it work. But luckily what we can do is we can do some factoring. Because over here, let's just note, if we take x squared minus 4, this is a polynomial that we can factor with a difference of squares. So we can say that x squared minus 4 is actually equal to x minus 2 times x plus 2. All right, and we can use this now and use this fact in order to compute this limit. So why is that? So first of all, no limit law here. This is just algebra. Just using that factorization, we see that we have this fact here. But now, where does this get us? Well, if we're approaching 2, how this works is that x can't be equal to 2. So notably, while we're computing this limit, the idea is that the quantity x minus 2 throughout is not 0. We can't divide by 0, but as we're computing this limit, we've sort of all agreed that x is not 2, so we can divide out by x minus 2 in the top and bottom. And that's going to give us that this thing is equal to just the limit as x goes to 2 of just x plus 2. But where does this get us? Well, where this gets us is now this is a function that doesn't have the same problem as the previous one. We can just plug the numbers in here, nothing turns into 0, everything's fine. So let's just do it with our limit laws, just because we're going slow to start. But indeed, just by the sum limit law and just the constant multiple limit law, we can break this into the limit as x goes to 2 of x plus the limit, let's say 2 times, the limit as x goes to 2 of 1, and these are sort of our basic atomic, simple as we can get limits. This just turns into 2 plus 2 times 1, which is 4. All right, so that's what we can do, even if you have a limit where you couldn't just plug the numbers in, because you get something bad like a 0 over 0 case, something like that. You can do a little bit of algebra to fix these things up to put it back into that case. All right, so now let's do 2 more examples. So first, let's do a similar one to the last one, but a little bit more complicated. Let's do the limit as x goes to 5 of x minus 5 all over x squared minus 4x minus 5. Okay, so, yes, so with this one, what we do is we look, and we can't just plug the numbers into this one either. We're going to get a problem. And again, what limit law this would violate is we can't just use the limit law to break this into a quotient right away, because looking forward, we see if we plugged 5 into the bottom, we'd get 25 minus 20 minus 5, and that would be 0. So we're going to have to do, again, the same sort of algebra that we did in the last time in order to break it up. So let's see how that goes. Well, what we'd really like to do is we'd like a factor of x minus 5 in the bottom. Well, do we have one? Well, it certainly looks like we do, because this polynomial, if you plug in 5, that gives you 0, so 5 is going to have to be a root. So what's the other root to this polynomial? Well, there are 2 things you can do. If you can't just immediately see a root quickly, of course, what you can always do is you can always just long divide the polynomial. If you long divide this polynomial by x minus 5, you'll get another polynomial as its quotient, and you'll see what it is. But another way to do it is you can just sort of eyeball these things. 0's not a root, 1's not a root, but if you plug -1 into here, you get 1 plus 4 minus 5, that's going to be 0. So indeed, various ways to do it, but one way or another, this guy is going to factor, and it is going to have a root of -1, so we get a factor of x plus 1 at the bottom. Now we can do the same thing as we did before, and we can just divide out by x minus 5 on the top and bottom, and what we get is, we just get that this is the same as the limit of 1 over x plus 1. And now, of course, we can use our quotient of limit laws to say that this is the limit as x goes to 5 of 1 all over the limit as x goes to 5 of x plus 1, and then just skipping one little step, plugging the numbers in, because we don't always have to be too on the ball about this. The limit is just going to be 1 over the limit of the bottom, which is 6, and that's our answer. Okay, so that's how we do this one. Same sort of thing as before, but we have to do a little bit of factoring. That's something that's going to show up here. There's definitely going to be a lot of factoring to do when we compute limits. Okay, so let's do another example that has just a couple more bells and whistles to it. Let's do the limit as x goes to 4 of x squared minus 4x all over the square root of x minus 2. All right, so the square root of x is actually one of these functions that's nice and continuous for numbers greater than or equal to 0. So it's another one of these things that we can just plug into. So we can work with it in general, but of course we can't work with it immediately here. We can't plug things into all of this immediately because the denominator is going to be 0. The square root of 4 minus 2 is of course 0. So let's do a little bit of algebra on this. So just as an aside, what this quantity is, if we take x squared minus 4x all over square root of x minus 2. I'm just doing some work over here so that I don't have to write limit as x goes to 4 every single time I do a manipulation. That's all, just a little bit of scratch work. So this thing we can see, well, upstairs, first of all, we might as well factor out an x. And that will leave us with an x minus 4 up top and a root x minus 2 in the bottom. So now what can we do with this? Well, note, one cute thing here is note that x is equal to the square root of x squared. So indeed, the top is actually a difference of squares. X minus 4 can actually be rewritten as the square root of x minus 2 times the square root of x plus 2. And of course we have our denominator here. And of course if x is not 4, we're going to be able to cancel off the top and bottom here. And that's exactly what we're going to do. So just plugging in this work over here, this limit, just by algebraic manipulation, is exactly the same as this thing here. All right, over this denominator. As we're computing a limit as x goes to 4, we are presupposing that x is not equal to 4, so we are not dividing anything by 0 if we cancel these factors off. So this gives us the limit as x goes to 4 of x times the square root of x plus 2. And now we have the product of limits theorem, sum of limits theorem here, and I've just told you that one of the things we can do, indeed, is that this square root of x is a function that we can just plug things into. So skipping a couple of steps, let's just say by various limit laws, which I just spoke out to you, we can just plug this number 4 into here. There's no problem there, and that's going to give us our limit. And that quantity is indeed 4 times the square root of 4 plus 2, which is going to be 4 times 4, which is going to be 16. So that's the value of this limit here, and this is why. We can use, often what's going to come up here is factoring, but just note that some things can secretly be differences of squares, even if they don't look like it at first.